Hello, this is Connor Hook. So first problem is called sleeping in an igloo. Basically, the internal convective heat coefficient is known, but the external heat coefficient is not. We just want to find what the internal temperature is inside the igloo. And also it's known that the floor is well insulated, and we know the outside temperature and things like that. So in this problem, we're going to be addressing conductive heat transfer through the snowpack, convective heat transfer, for the air on the inside and on the outside of the walls. Resistance networks for 1D steady state problems. So this is a steady state 1D spherical problem to find internal temperature with a resistance model. Spherical coordinate system, obviously Cartesian coordinates are not ideal for hemisphere, and external forced convective heat transfer. So we know that the velocity of the wind speed is about 3 meters per second. Constantly throughout the night, and we just have to find the convective heat transfer term there. And I just have some sources where I wanted reasonable values in that image. So first of all of our knowns, we're going to assume some fairly large assumptions. For example, the Nusselt equation is valid not just for a sphere but also for a hemisphere. Reasonable assumptions, but some error can crop up in there. These are the properties of air at the temperature, outside temperature, and at 1 bar. Okay, so first of all, we're going to find the Reynolds number. We find it's around 700,000, very turbulent flow. So we're just going to use Whittaker's equation as shown in the textbook to find the Nusselt number. We do have to use a lot of, caution with this equation, because obviously it's made not just for spheres, but also for spheres of Reynolds number capping at around 80,000. So we just have to be aware that this could give us erroneous values. What we find is that from this Nusselt number calculated out, it gives us an expected H value of around 5 or 6 watts per meter squared times Kelvin. And this is perfectly reasonable. Next, we're just going to set up a quick resistance model. Both the convective terms are very straightforward. The only exception is the conductive through the snow, and the reason is because it's through a hemisphere. So we just have to go back to Fourier's law of heat transfer, slap in the surface area as a function of radius into this area piece, and then integrate it, and we get an equation that is functionally the same as the resistance model for a sphere. The only difference is that, of course, it's going to have half the total surface area. And this is valid because we're assuming that there's no heat leaving through the bottom. So from this resistance model, and knowing that he's going to be burning about 2,500 calories in 24 hours, which works out to about 120 watts, we end that reasonable indoor temperature for his igloo is around 4 degrees Celsius, which is pretty toast. So secondly, we've got Andrew's adventure. So Andrew's going to go on a little adventure, an adventure into the center of his mind, because he's having a rough semester at Mines. Aside from letting his kitchen slip a little bit, he's celebrating Christmas over spring break. It's just not going well for Andrew. So he pulls his groceries out of the oven. He forgot it. He left it in there before he went for a nap. And he's going to pull out a nice hot can of root beer and hang it as a Christmas ornament. And this question is basically just, how long does it take for the center of this drink to reach room temperature, technically within 1 degree of room temperature. And then we're going to analyze it as a lumped analysis, long cylinder, and a short cylinder. And importantly, there's natural convection. There's no given convective heat transfer term or anything like that. So obviously this problem is going to address the learning objectives of lumped analysis, 1D conduction, and 2D conduction, and for cylindrical coordinates here, and natural convection heat transfer. And that's actually what makes this problem quite complicated, because you'll notice there's not a constant surface temperature, it's transient. And secondly, there's not a constant heat flux going through this. That's also a function of temperature. For sources, I just assumed that values like heat capacity and things like that, I couldn't find them for root beer exactly. I just assumed they were similar to those of sugar water, which about 10 degrees Brix. The first step is that we are going to try to find a approximate H value that we could use as constant throughout the whole problem. That's going to get us in the right ballpark. This equation, which is designed for a hot vertical plate, we were told that we can use it in this condition when diameter is greater than or equal to 35 times the length over the Grashlet number or whatever, and that's not true in this case. But because this is such a ballpark estimate in the first place, it's totally fine. It's going to get us in the right ballpark. Calculating this out, we find this is at time at t equals 0. For these temperature values, we find that the Nusselt number is about 32, and therefore the convective heat transfer term on this can of soda is going to be about 7.5 watts per meter squared times Kelvin, which seems pretty reasonable considering how hot it is. There's probably going to be a lot of air circulation, so pretty reasonable term. And then we're going to run these calculations again once the temperature has cooled down halfway, and we find that at that point the H value is around 6 watts per meter squared. So so I just assumed that we can proceed assuming that throughout this entire problem there's going to be a constant H value around 6.5 watts per meter squared times Kelvin. This obviously is going to, procure some error, but these are the sacrifices you have to make when you're bravely solving for how long it's going to take for your Christmas ornaments to cool down. So first, just going to perform a lumped analysis. Very straightforward. Calculate the B out number with the critical length being the ratio of volume to surface area. We find that the B out number is indicative of a pretty accurate lumped analysis. So we expect this to be similar to our other more in-depth calculations. And we find that it's going to take a period of roughly 10 hours. Next, we're going to assume this is a long cylinder, which of course is not true. A can of soda is almost as wide as it is tall, but don't worry about it. Interpolating from handout number 8, we can find these coefficient values from these properties of sugar water and root beer. We can find the thermal diffusivity, and just plugging and chugging everything in. In this case, we find that the expected time to cool down is around 14 hours. So a little longer before you can grab and slurp that delicious ornament. And then lastly, we're going to do it with a short cylinder. We're just going to be doing the product rule between a long cylinder and a wall. So the cylinder part's going to be the same as I just discussed here. The wall part's going to be very similar, and we're going to be discussing the center part, not only because it makes the math easier, that's the main reason why I did it, but also because that's going to be the hottest part of the soda. And we're not trying to cheat here, we're trying to get when the middle of the soda is cooled down. So from the B out number here, and from the same table in the handout, we can find that according to this method, it's going to take around 11.5 hours. So based on our roughly ballpark calculations at the beginning, we can't take any of these numbers to be too precise, but I think it's fair to say that we can expect it's going to take around 10 to 14 hours for this Christmas ornament to cool down. In any case, hopefully I didn't go too far over. Tried to spice this up a little bit because I know grading things is boring. Yeah, thanks for watching. Yeah, that's all I got.